Earth by altering the cloud properties. Now, what is cloud condensation nuclei or CCN? In real atmosphere, water vapor needs some surface to condense and form a cloud droplet. So those aerosols are known as the cloud condensation nuclei. So when the size of the cloud condensation nuclei are big and they are less in number, the surface area will be less and the cloud reflectivity will be also less. But when the number of the CCN will be high and the size will be also less, the surface area will be high and the cloud will reflect more solar radiation. So this is how, by altering the cloud properties, aerosol can also alter the radiative balance of the Earth. Now you all know that aerosol have severe health effect, and the more finer the aerosol can penetrate more into the human respiratory system. So both the climate and health effect of aerosol depends mainly on two factors. One is size and another is chemistry. Thus, to evaluate this health and climatic effect, it is very important to gather its size, a proper long-term size segregated chemistry of aerosol in different atmospheric environment. This kind of work has been conducted in some place of the world, but this kind of data, especially size segregated characterization of aerosol, is rare in Indian context, especially the Eastern India till date remains very virgin. So we had taken three absolutely different atmospheric environment. Two of them, one is Himalayan environment and another is mangrove ecosystem. These two environments are very, very ecologically rich and they are very, very vulnerable in context of climate change. In addition, we have also conducted our study over a tropical urban atmosphere, Kolkata, where 4.5 million people lives, and air pollution is a serious concerning thing for their health. So in these three sites, we have conducted our study. We have collected aerosol using this instrument, and their samples were chemically analyzed for water soluble major ion, water soluble organic carbon, and then the optical attenuation for the brown carbons. Now, what is brown carbons? Decades before, scientists usually believed that the black carbon usually absorbs the sunlight and they warm the atmosphere, while the organic carbons usually scatter the sunlight and cool down the atmosphere. And they put those data on the radiative model to calculate the net radiative effect of the aerosol. But nowadays, scientists have discovered that there are some organic compounds, which actually absorbs the solar radiation and contribute in global warming. Those are known as the brown carbon. So it is extremely important to eliminate the uncertainties in the radiative model to have a proper knowledge about the optical attenuation property of those brown carbons. Now, these are the air mass back trajectory computed from various models to observe the influence of the long range transport of the aerosols. So the upper panel is for Darjeeling and the lower panel is for Kolkata. The red dots represents the active fire counts which we have retrieved from the satellite observation. The black lines correspond to the lower level air mass which can take more pollution as they are near surface, while the yellow lines are the upper altitude air mass. You can see that over Darjeeling and Kolkata, both Darjeeling and Kolkata receives biomass burning plume during the pre-monsoon time. Darjeeling receives the biomass burning plumes of Nepal and Upper Indo-Gangetic Plain, while Kolkata receives biomass burning plumes from the eastern coast of the India. During monsoon, both the station receives marine influence aerosol, and during post-monsoon and winter, both the stations receives continental haze from Indo-Gangetic Plain. Now, these are the aerosol mass concentration over Darjeeling and the mass size distribution of aerosol over Darjeeling and Kolkata. You can see over Darjeeling, pre-monsoon time and winter time are the most polluted in the year. During pre-monsoon, it is a very common tourist place in Darjeeling, and the hill receives a very high amount of tourist-related emissions, and with that, the long-range transport of biomass burning plume from the Nepal and Indo-Gangetic Plain increases the pollution load during the pre-monsoon, while during the winter, domestic heating related biomass burning can cause this increase in aerosol loading. if you observe this size distribution pattern in all 4 seasons, Darjeeling shows the Himalayan atmosphere. Darjeeling shows a bimodal distribution pattern with prominent fine mode peak. In case of Kolkata, you can see the post-monsoon and winter are the most polluted seasons in the year, and you can see that fine mode aerosol. For the fine mode aerosols were dominant during the post-monsoon and winter. The black lines are for the winters, and the green is for post-monsoon. And while in post-monsoon and in monsoon and pre-monsoon, coarse and fine mode peaks contributed almost equally. Now, this seasonal variation can be attributable from seasonal source profile and long-range transport for Darjeeling. And in case of Kolkata, where the source remains same for the year, this seasonal variability can be attributable from local meteorological condition and long-range transport. Now, these are the major water-soluble ions found over Darjeeling and Kolkata. You can see the similarity of sulfate, nitrate, and ammonium found in both Darjeeling and Kolkata. These are basically the secondary species. That means they are formed within the atmosphere. And the fourth one is non-sea salt potassium, which is a very reliable biomass burning tracer. And biomass burning tracer, the red lines are for the pre-monsoon, while the black lines are for the winter. So during pre-monsoon and winter, the biomass burning aerosols dominate in the environment of Darjeeling. And calcium, which is a very good tracer of dust particles. You can see the green lines correspond to the post-monsoon and black for the winter. You can see a coarse mode peak in the coarse mode peaks. This corresponds to the paved road dust, while the fine mode peak corresponds to the transported dust. So the aerosol during this time is mainly influenced by the transported and paved dust over Kolkata. Now, coming to the water-soluble organic carbon, you can see no distinct seasonal variation was observed over Darjeeling in any season. But if you observe the light absorption efficiency or mass absorption efficiency of Darjeeling, you can easily find that winter time they are more light absorbing. That means the local biomass burning aerosol were more light absorbing compared to the other seasons. While distinct seasonal variation was observed in Kolkata, you can see that post-monsoon and winter shows high concentration. But if you look at the mass absorption efficiency of the brown carbon, water-soluble brown carbon, you can see that during pre-monsoon, it is high compared to the other season. That means the long-range transported biomass from the Eastern Ghat were more light absorbing than compared to the continental haze. Now, this is a very common phenomenon. Every year we observe in newspaper the crop residue burning of Punjab and Haryana and consequences air pollution over Delhi. Now, very few of us know that this kind of thing also happens over Eastern Ghat region, and the downwind places like Sundarban and Kolkata faces the consequences like this. And these are the air mass back trajectory models for over Kolkata for early summer and late summer. The only difference you can see that during early summer, this is high in active fire spots compared to the late summer, and you can see that it is the fine mode concentration of aerosol during the fire episode is almost 3 to 4 times high compared to the other season. And not only the concentration, if you look very closely, the size distribution pattern was coarse mode dominant environment in normal episode, and it changed to the fine mode dominance environment in fire episode. So in a city like Kolkata, where air pollution is a major thing to concern, it is not only changing the concentration but also altering. The additional source is also altering the size distribution pattern of the aerosols too. As I earlier mentioned, that potassium is an excellent biomass burning tracer. You can see that enhancement of potassium. This further proves the influence of biomass burning aerosol during that time, and it also increases the carcinogenic polynuclear aromatic hydrocarbon. So health-related hazard also increases during the biomass burning period. Now, this is sea salt, and sea salt acts as a brilliant cloud condensation nuclei.
Sorry, 2 more minutes. Sorry.
Okay. But they act as a brilliant cloud condensation nuclei. But when these sea salts in a humid condition, they react with the inorganic or organic anthropogenic acids, and they forms modified sea salt and release hydrochloric acid. This phenomenon is known as the chloride depletion, and we measured it how. The mass ratio of chloride to sodium in reference seawater is 1.81. So we from ion chromatograph we get this data of sodium, and from that hypothetically we calculate how much chloride there should be and how much chloride we get. From there, that we calculate the amount of chloride depletion. And now when the smaller sea salt actually reacts with this anthropogenic species, they get bigger and bigger, and they undergo hygroscopic growth and get deposited. So this can also alter the sulfur and nitrogen cycle also. Published this paper in Chemosphere this year. This is for the first time ever in the world we have proposed five different in situ reaction mechanism by which the inorganic acid, sulfuric acid, and nitric acid actually actually modified the sea salt based on the stoichiometric condition of the acids and base, and based on the stoichiometric condition of the acid and basic vapors. And then we follow some basic chemical steps and logical steps to determine which reaction pathway actually was reasonable for the chloride depletion. And what we found over Darjeeling and Kolkata, the larger particles were neutralized mainly because of the nitric acid, while the smaller particles were neutralized by the partially neutralized sulfuric acid. In case of Sundarban, the inorganic acids was not enough to account all the chloride depletion that was observed. That means some other species were also involved in the chloride depletion in Sundarban. Those might be organic acid of the mangrove ecosystem. Another important observation was there during the Eastern Ghat Eastern Ghat biomass burning period, the acid concentration over Sundarban was double compared to Kolkata. This proves that the mangrove ecosystem actually acts as a sink of those inorganic acids and inhibit their further advection towards Kolkata megacity, where air pollution is a serious concern. These are some outputs I have produced till date in last 5 or 5.5 years, and some recommendations like awareness program from school level, some alternate resource of livelihoods, plantation of more mangroves, more investment on public transport, usage of less consuming electronic appliances, and introducing green tax, because I firmly believe that we, the so-called privileged urban people, are doing this nonsense, and these people are actually facing the consequences. And with that, I'd like to thank and ready to take your questions.
So, thank you. The session is now open for questions.
Hello?
Yeah, I just have one question. So you may show some statistics and the data you collected from Darjeeling or Kolkata. So how do you get those data? Is it satellite data you gather from?
No. Those all were in situ data. We have collected size segregated aerosol. I have shown those instruments. Let me just show you. Yeah. So these are the two major instruments by which we have collected the size segregated data. This is a 11-stage cascade impactor. This provides you the size segregated aerosols of different layer, and those this is ion chromatograph and TOC analyzer by which we get the major water soluble ions and what total composite water soluble organic carbon by this, and this is the liquid wave guided capillary cell by which we measure the optical attenuation.
Okay.
I am Gautam Gangopad. I have a question. You showed those 5 pathways.
Yeah.
So and said that you are the first person to, you are the first group to present it. Yeah. So my question is, how did you come across these pathways? Are they exhausted, or can there be any more?
Yeah. I don't get you. Please, can you repeat your question?
Question is, you said that these are the only 5 pathways, and then you are looking for which one is the prominent one in your work in this region. But my question was that how did you come in? Were these pathways known, or were you the first to propose it? Number one, and
we are the first group to propose this kind of in situ reaction pathways. Okay, and then we are also the first group who actually identified who stepwise screened those pathways and determined and shows that which pathways is actually playing the vital role.
And second question was, is this exhaustive, or can there be any other pathway also?
Yeah, there can be there can be other pathways also, because we have only taken the inorganic acid. If you see this slide, I have written that over Sundarban some other species were also involved. So there might be some other inorganic or organic acids which we don't consider, which were beyond the scope of this study. So there might be some other pathways, but we take those two major inorganic acids which are the most abundant one in the atmosphere, in the real atmosphere.
The Sundarban data is for sea salt.
Yeah. Sea salt chloride depletion chloride.
Okay.
Sodium chloride.
Abhinandan, this is Ranjan.
Yeah, sir.
I have, instead of question, it's a kind of a comment.
Okay.
So what you have presented is actually kind of an observational study. Am I right?
Yeah. Yeah.
And then I just asking you your comment, your opinion, how your study is unique or different from already published data.
This is the first time for. First of all, I make that comment that size segregated data on size segregated aerosol chemistry is very rare in Indian context, and this is the first time ever this kind of study has been conducted for Himalayan atmosphere as well as over an mangrove ecosystem. Secondly, as I already have mentioned, this is the first time some in situ chemical reaction has been proposed for sea salt chloride depletion, and sea salt acts as a brilliant top condensation nuclei. And so this type of this kind of anthropogenic interaction with the sea salts can alter the cloud properties as well as the rainfall pattern. So these are very unique in nature. And another thing is that we all are very concerned about that Punjab Haryana incident, but very few of us actually know that due to the shifting cultivation by the tribals of Eastern Ghat, Sundarban and Kolkata is also facing a deep problem. And Sundarban is a climatically extremely vulnerable region where this kind of sea salt chloride depletion and all the size distribution pattern, mass size distribution pattern change can cause very severe climatic effect. So these are in these terms, this study is very unique, and thereafter, this is the first time ever in the Indian context anyone has studied size segregated light absorption of brown carbons, which is a very new term in context of aerosol chemistry.
That is fine, but to the point is, in case of Punjab and Haryana, is a biomass and the impact to the environment, right? That is one thing.
Yeah.
That can be seen visibly. I mean, it's in our naked eyes, every day's experience.
Yeah.
And I would have been loved to hear from you that with your study, you can predict and use as a forerunner or kind of a whistleblower for environmental problems.
Okay, so that can be done, but I was not focused about that. But one thing, if you observe it very closely, that this phenomenon, this biomass bonding phenomenon of Eastern Ghat actually occurs during the pre-monsoon time when the atmosphere remains, the wind speed is high, the mixing layer depth is also very high. So the dispersion condition is very good that time. If this phenomenon happen during the heavier months, I mean during the winter or the post-monsoon, this might be also a case like Delhi. But the weather here favors us, but still you can see that how much concentration is changed and how much the size distribution pattern is changed. But yes, it's a point that in future it can be think about that to forecast the aerosol. But I don't have that. I have not that expertise. But yes, our group is trying to do those kind of things to predict the air pollution parameters. Okay.
So, Abhinandan, I have a question that is not much related to what you have been doing, but for last few months we have been listening that aerosol can stay in air for certain period of time.
Yes, sir. I cannot hear you properly, sir. Can you repeat, please?
Yeah, but in today's context, aerosol is coming, getting some importance in relation to COVID infection. So what we get to see from TV that it can stay in circulation for a certain period of time, and it can go that far. Could you enlighten us that really size and shape and how much it really reflects on the how long it can stay in the air and can transmit the infection?
This needs a long-term exposure data of this aerosol. I should not comment so lightly on this topic, but yes, the aerosol have severe health effects, so it might have an effect on. But with this amount of data, I should not comment on that on this that these aerosols are how much time we should get exposed in the air. I should not comment on this. This need long-term data and
so another question, that this aerosol, because it contains some acid, and how much during rainy season it must be coming to the ground, right, on the soil. So it must have some reflection on the crops and vegetables growth. Do you think it has some impact on that?
Definitely. When the smaller aerosols get with hygroscopic growth and other chemical transformation, they get deposited on soil. I have mentioned that word, that when the sea salts getting reacted with the inorganic acids and forming the sodium nitrate or sodium sulfate, and they get deposited in the soil, they can alter the sulfur nitrogen cycle also. Similarly, when the black carbon aerosols get deposited over the leaves or the crops, the photosynthesis also may get affected. So definitely there is an effect.
Okay. Thank you.
Thank you, Abhinandan. I just have one comment. I'm not a part of the judging team, so my comment or your answer to the comment should not affect my judgment. So what you showed was sea salt depletion, right? And this should be a general phenomenon applicable to anywhere in the world where there is a coastal area and where there is biomass burning and the right kind of wind, right?
Yeah, not only biomass burning, but any emission from any anthropogenic acid emission.
That's correct. So my comment is, if you have, probably you already did it, but if you have not done it, it would probably benefit you if you think of any other geographical, places around the world where there is sea coast and anthropomorphic, activity, and such effects might be applicable there. That's just a comment, okay?
Okay. Thank you, sir.
So thank you, Abhinandan. Next we have Orko Prabho.
Yes, sir. Am I audible?
Yes. So get ready. Orko Prabho Ghoshal will be speaking on quantum teleportation and fluctuation. So quantum teleportation and fluctuation by Orko Prabho Ghoshal.
Yes, sir. So may I start?
Yes.
Okay. Okay. Good afternoon, everyone. My name is Orko Prabho Ghoshal, and my supervisor is Professor Shonshu Prabhandopadhyay. Today, I will going to talk about quantum teleportation and fluctuation. At first, let us start with this particular picture. Your town area, and his intention is to go some mountain or forest area that is mile apart. Okay. Now the problem is that he cannot afford any kind of vehicle. Okay. So any kind of taxi or train is not is completely forbidden for him. So any kind of physical transfer is completely forbidden for him. Now the question is that, is it possible to transfer any physical information without any physical transfer? Now, in reality, it seems to be impossible, since maybe it violates some natural laws. But surprisingly, quantum physicists have experimentally demonstrated that it can be proved and it can be shown that quantum teleportation is possible. So, but only in quote-unquote quantum domain. So before going to my work, let us try to motivate the basic ground of teleportation. So the basic definition of quantum teleportation is that transferring an unknown quantum state which contains some physical information without any physical transfer. Now, what is the importance of quantum teleportation? The first importance is that it is an efficient protocol ever for information transfer. So it is the most efficient protocol than any classical possible strategy, and it doesn't require a large amount of classical communication cost. Now, for example, consider this type of a network. Okay, so this type of complicated network where, for example, from this station, I want to communicate with her. Now, maintaining some algorithm, it may cost a large amount of classical data or classical info or classical channel. But if that thing is replaced by quantum teleportation, then it can be shown that on using only 2 bits of classical communication, we can faithfully achieve quantum teleportation. That means we can transfer any physical information from this station to that station. And the third importance is that it is enough secure protocol than a direct physical transfer. So that means if I want to transfer any kind of information, any kind of physical information, I must encode that information in some physical object, and then I use some channel to send my object to somewhere else. Now, this is a very risky case, since there can be hacking, there can be eavesdropping, but teleportation is much more secure protocol than that. So these are basically important things. Now let us move towards quantum domain. So in quantum domain, we have to deal with subatomic particles. That means quantum particles like electrons, like photons, like protons. So these particles can be think of like quantum bits. So quantum bits carries actually quantum information. So quantum bits are physical objects with 2 energy levels or 2 degrees of freedom. Uh, there is a particular difference between quantum bits and classical bits. That quantum bits can contain more information than a classical bit can. For example, a classical bit can take only 2 possible values: a zero or a one. Okay, so either the ground state or a excited state. But quantum bit can more information than a classical bit. Let us give some experimental scenario. This is the well-known Stern-Gerlach apparatus where there is some oven and this blue line representing beam of particles or beam of subatomic particles. That means beam of electrons, for example. And this is collimated to a particular beam split. After passing through this beam splitter, we have 2 possible paths. The upward path represents the 0 state and the downward path represents the 1 state. So before entering the beam splitter, a general qubit state can be written as a linear superposition of 2 possible energy levels or 2 possible degrees of freedom, where these x and y are basically arbitrary complex numbers which obeys some kind of normalization condition. So if this is a simple equation of a circle, a unit circle. Now the problem is that for a given energy levels, we can have infinite number of possible quantum states, which gives some advantage than a classical bit can. Okay, so let us move towards quantum teleportation. Let us define a game. Let us play a game. The name of the game is how better can you guess an unknown quantum state. So this is the building block of quantum teleportation. Suppose we have an information source, okay, and we have 2 players, 2 celebrities. Each celebrities can access 2 subatomic particles or 2 quantum particles. Okay. Now an unknown qubit state or an unknown particle is given to Mr. Kumar. Now another particle is given to Mr. Chatterjee. Okay. Now, Mr. Chatterjee has no idea about the qubit state given to Mr. Kumar, as well as Mr. Kumar doesn't know what qubit state he picked up from that information source. Now, he asked Mr. Chatterjee that guess my state, what is my state? But without any cooperation, Mr. Chatterjee cannot do any guess, any proper guess. So he said that at least give some clue. So in that case, the average guessing will be 50%. Okay. But certainly Mr. Kumar, which is Mrs. Sen. So after seeing Mrs. Sen, he wants to collaborate with him. Okay. So he actually, Mrs. Kumar, do that something that Mrs. Kumar chooses some particular reference frame and communicates the reference frame to Mrs. Sen that please measure along this z-axis. Now, Mrs. Sen has some another particle with her, and Mrs. Sen actually measured the third particle with respect to the reference frame chosen by Mr. Kumar. In that case, surprisingly, the average is increased from 50% to 66.7%. But that was close enough, but that was not enough. Now, Mrs. Sen wants to guess accurately what is the state or what is the quantum particle given to Mr. Kumar. But unfortunately, since this qubit is completely unknown to everyone, so it cannot be properly guessed. And there are infinite possible quantum states for two energy levels, as I mentioned earlier. So even if they share infinite number of classical channels between them, they cannot increase the efficiency beyond 66.67%. But this is the limitation of classical theory, and this is the limitation that I cannot faithfully transfer any physical correlation or any physical information from Mr. Kumar lab to Mrs. Sen lab. Now, what should they do? So they meet with Mr. Bhanu, and Mr. Bhanu is a physicist. So he actually prepared an entangled state. An entangled state means that the two particle state between two subatomic particles which maintain some kind of quantum correlation. Okay. So its singlet state can be written like this. It's a two-particle state, and one particle is given to Mr. Kumar, and another particle is given to Mrs. Sen. Now, what they do? Mr. Kumar actually do some joint measurement on the unknown qubit state picked up by him and the particle given to him. And after the operation, he actually broadcast the message using two classical beats to Mrs. Sen. And after hearing from Mr. Kumar, Mrs. Sen does some operation on the particle given to her. And after that, the average guessing surprisingly increases to 100%. Okay, so no infinite amount of classical communication is required here. On using only 2 bits of classical communication, a teleportation happened. So this is actually a teleportation. That means the qubit state is not physically transferred to Mr. Kumar lab to Mrs. Sen lab, but the information contained in that qubit is transferred to Mrs. Sen lab, surprisingly. So this is actually a teleportation. Now our problem is based with noise, the effect of noise. Now these entangled states are very fragile in nature, and the noise or the environment quickly interacts with them, since these are subatomic particles. Now there are many noisy scenarios. So noise is a general structure. So there can be any possible noise. So it will be a good problem if we want to characterize quantum teleportation and chooses the best performing entangled states for noisy scenario, which are optimal for quantum teleportation. So in case of noisy entangled states, in case of noise, the guessing power decreases from 100% to a lesser value, and as well as some kind of fluctuation arises while you guess. Now this fluctuation, the arising of this fluctuation is obvious, since when there is noise, there is some statistical uncertainty, and due to the statistical uncertainty, we face with fluctuation. Now the problem is that we have to choose cleverly such noisy entangled states for which the average guessing doesn't go below 66.67%. That is the classical bound. If they go below 66.67%, it will be a meaningless. We always want some quantum advantage above classical physics or above classical strategies. So we actually define two proper quantifier that characterizes quantum teleportation. The first quantifier is the average fidelity, and the second quantifier is the fluctuation while you guess. So what is average fidelity? Average fidelity is the average guessing or closeness between the input and the output state. The input state chosen by Mr. Kumar and the output state which guessed by Mr. Sen. Okay. So this average fidelity can be increased under a well-defined strategy. And this this fidelity can attain a maximal value that is strictly greater than 0.667, that is the classical bound. And for that particular maximal fidelity, we get some fluctuation. So what is fluctuation? Fluctuation is basically the standard deviation of guessing about the average value. So just look at this particular sphere. So this sphere represents a subatomic particle. But different, it is that different region actually contributes differently while you guess. Okay. So due to this particular case, a fluctuation arises. And in only noisy case scenario, we get non-zero fluctuation. So actually, in our first result, we accurately characterize quantum teleportation for a general noisy scenario, and we accurately get the exact value of this fluctuation for any general qubit state.
Okay,
The
Prabhu,
next task.
stop. You better finish quickly.
Okay. The next task is to choose the optimal states for quantum teleportation. Which are the best states for quantum teleportation? Now, these we have get a hierarchy. So this pink region is the useless channel for quantum teleportation, and maintaining a hierarchy, we get optimal states. These are optimal states for quantum teleportation, for which the fidelity is maximum, the guessing power is maximum, and there is no fluctuation. And these states are luckily are noisy entangled states. So noise helps to perform quantum teleportation far better than noiseless scenario. That is an interesting result. And what is the summary? Teleportation can be completely characterized by maximum fidelity and fluctuation in fidelity. And fluctuation in fidelity has no relation with any experimental error. It is a property of the state indeed. An entangled state is useful and universal for teleportation if the maximal fidelity is greater than classical bound and deviation is zero. And the optimal states for teleportation are typically noisy entangled states. All these results are published in these three papers. Okay, so in these three papers, we have established a complete theory that how we characterize and how to find the optimal states for quantum teleportation. So these are the publications, and I'm thankful to my institute, my supervisor, for giving me the opportunities. And these are my collaborators: Devorshida, Shopdorshi, Oru, Prosenjit, Kudavaditya Bej. Thank you.
So thank you, Suprabha. Now it is open for discussion.
Yes.
Subhendra, you are there?
Yeah, I'm there. I'm just not really sure what I'm asking. I do understand properly, but my point is that you probably done it in a, I think, theoretical way. That you have calculated this kind of teleportation concept.
Yes, sir. Yes.
So, can you let us know about any kind of experiments that can be done to check that?
Yes, sir. Obviously. Actually, to perform experiment, we have to do a long-range quantum communication. That means there may be two possible labs, one situated in India and another situated in somewhere else in America. And there may be some satellite which actually create some kind of entangled states. Entangled states means some kind of subatomic particles, and using some kind of channels, these particles must be shared between two labs. And using this shared correlation, we can securely transfer any kind of physical correlation. So it is very useful for fast communication or broadcasting any particular information securely. And it is proved experimentally, and it is published in Nature. Then how to experimentally demonstrate teleportation, but that is quite technical to prove.
Arindam?
It's a good talk, Arkaprabha. I want to know, I'm a novice in this subject. Actually, the thing is, see, this communication, telecommunication, and all these things, wireless communication has been known to us. Correct?
Yes.
If you want to send some email from one corner of the world to the other corner of the world, it is also there. So how does your research will help to improve that things? Already we have reached to a state that is optimal. Can you please make
Sure.
us understand
Sure,
it
sure,
is not a sheer calculation and all these things.
sure.
What is the practicality of your calculation?
The main practicality is that it is much more secure than look that this
If we send some information through emails with some code and all these things, that is also secure. For example, I have sent one PDF file with some code number. Unless my friend doesn't know this code number, he or she is unable to open this file.
Right.
Correct?
Exactly. But the problem.
So is it accuracy? Is it the information accuracy?
Yes, sir. Actually, the
Because
guy.
that basic thing has been known for a century. Even the institute which you belong to, the great Jagadish Chandra Bose, he did this experiment more than a century ago.
In the
Very good. But thing is,
classical computers, we use RSA security system. So that means we have to factorize a prime number. Okay, so the hackers are far clever enough that they can actually do some algorithm, and after doing that algorithm, they can factorize that particular code. And if they factorize, they hack the system. So this RSA security system is much more secure, but it can be hacked. But while you do teleportation, that is much more secure. The reason is that when you send information from one part to another part, there may be hacking, there may be eavesdropping. But in case you share some fundamental physical correlation between one lab and another lab, there is you cannot even hack the systems. It is impossible, because if you hack.
that is very good for your this defense and our banking system technology. It can be implemented, but the thing is, if it from one person to another person, say for example, is it for A to B or A to many? In today's technology is concerned.
Yes, we can actually define it a quantum network
What
structure.
I have understood, that is some limitation from point A to point B, not from point A, it is diverging to many. Correct?
Right.
Okay, so Gautam Gangopadhyay.
Yeah, I have just one or two questions. First of all, is that how come that f is less than 1 and yet delta is becoming 0?
Okay, so this F is actually the casing power or the maximum fidelity, that how fluctuation actually arises. So fluctuation has no relation with experimental error. It is due to the uncertainty of the noise, physical noise, which interacts with the entangled state.
Yeah. But my question was, if delta is 0, then how can f be less than 1? That was the question. But I couldn't understand that.
Sorry. So if delta is equal to 0, that means there is no fluctuation. That means every state is teleported equally well. But
So in that case, yeah.
Yes, but in that case, it can be shown that since those states are basically noisy entangled states with zero amount of fluctuation, the maximal fidelity or the casing power is still less than 1. So the reason behind that is the monogamy of entanglement. So monogamy of entanglement is responsible for this feature. That means if noise reduces the entanglement or reduces the power of the strain, then due to that reason, you cannot guess properly. But still, you can the fluctuation can be zero also.
Okay. So that's why what you mean when the noisy entangled state may be better than noiseless state.
Right.
Yeah. Right. Okay, thank you.
Ranjan?
This is Ranjan.
Yes, sir.
I am actually from the biological field.
Yes.
So it's interesting to listening to your talk. I was just thinking, your teleportation, the concept, if we apply in today's context, means
Yes, sir.
you are connected from some place and we are also from different places. What benefit
Yes.
would we get?
The basic benefit is that it caused the classical communication. I mean, in today's scenario, when we are dealing with complicated network or internet,
No, just a moment. Just think about we are talking from different places.
okay,
And if we apply your concept of
yes,
teleportation for this kind of
yes.
presentation, what benefit would we get?
Well, the main benefit is that I can send any letter or any kind of picture or any kind of information securely to you.
Only
So that is the only benefit, and there may be no chance of hacking that information. So that is the main benefit. So otherwise there can be eavesdropping, but you can avoid those kind of eavesdropping or hacking if you use this kind of shared quantum correlation. Uh, Actually, but this is a strange thing, but it can be done.
okay.
Okay. Thank you, Arka Prabhu.
Okay, thank you.
Uttam?
Yeah.
Okay. Swayam and
Procheta. So, Procheta, are you there? Procheta.
Yes.
Okay. So, I've lost some paper, but I think you will be talking about something with StatMech. What was your topic?
No, my topic is quark-gluon interaction.
Sorry, quark-gluon interaction. I'm sorry.
Yes.
So, Procheta Shingo is our next speaker, and she will be talking on quark-gluon interaction. Procheta.
So, hello everyone, this is Procheta Shingo, and today I will talk about quark-gluon interaction. My PhD supervisor is Professor Rajesh Shire, and let me start with a very known picture to all of us. This is the phase diagram of water, where different phases of water is shown depending on various control parameters like temperature along the x-axis and pressure along the y-axis. And we know for a fixed pressure, if we try to go from ice to water, whenever we cross this phase boundary, we will see a phase transition. So same goes for when we are trying to go from water to steam, etc. But what happens when there is no phase boundary, like beyond this critical point? There, one can continuously go from one phase to another without any phase transition, and to distinguish it from this phase transition, we then call it a crossover transition. Now, with this quick recapitulation, let me introduce to you another phase diagram where we have temperature along the y-axis and chemical potential along the x-axis. Now, among various phases shown here, I will only talk about this hadron gas phase and this quark-gluon plasma phase. Now, what is this hadrons? Two very known hadrons to us is proton and neutron that resides inside the nucleus. Them and many other friends of theirs, they all together forms the hadron family. And it has been long known that these hadrons are not elementary particles like electrons. Rather, inside these hadrons, one can see quarks and gluons who are behaving like free particles. Now that we know these hadrons are composite particles, if we can supply sufficient energy to them, they will eventually break down to its constituent particles. Now, when we talk about the sufficient energy in terms of temperature, this temperature is around 10 to the power 14 Kelvin. So the only physical scenario where we can expect this temperature to exist is the very early stage of the evolution of universe. And that's what makes the study of quark-gluon plasma interesting, because then we can say something about the early stage of the universe we had. So, but how can we create this extreme condition here in the laboratory? For this, these heavy ion collider experiments come into play. Now, this is a basic working principle of these heavy ion collider experiments, where two relativistically accelerated nuclei collide with each other, and due to their collision, very high amount of energy is deposited in a very small region of space and time. Now, this extreme energy density will then give us an perfect atmosphere where the quark gluon plasma can be produced. And this quark gluon plasma, once they are produced, the medium constituents continuously interact with each other, and following the laws of relativistic hydrodynamics, they will then expand in size, they will cool down, and they will get more dilated. That is, we are going now downwards along this temperature axis. So obviously, at somewhere we will find this crossover. So from quark gluon phase here, we will go to the hadron phase, and even in the hadron phase, particles will continue to interact with each other unless the system gets so diluted that the particle mean free paths will get comparable to the system size, and they will then cease any kind of interaction, and then those particles will free stream towards a detector, and then they will be collected. Now, what we do from theory side is we try to see the behavior, how the particles are interacting in this quark gluon plasma phase, and how this can be related to the experimental data. Now, for that, to learn about these interactions of quarks and gluon, the basic theory we have with us is quantum chromodynamics. Quantum chromodynamics tells us that if in our medium we have quarks and gluon, these are three basic interactions that we can expect to have. Now, with each this junction here shown, we can associate a coupling constant, a coupling strength. Now, it can be theoretically shown that if there is a coupling strength of, say, G, there would be G, and there the strength will be G square, and so on. However, let's think of a scenario when we want to collect only these three gluon interaction terms. So we know my initial and final particles are gluons, but along with this simple interaction diagram, we can actually include many other diagrams of higher order. Like here, we have only included next to leading order. We are calling it a leading order diagram, and here we have included next to leading order diagrams, where we can see the number of junction has increases. That means we have now higher order of coupling strength terms. Like this, we can also include next to next leading order diagrams, and so on and so forth. So how to theoretically handle it? Now we have two basic principle-based theoretical approaches. First one is the perturbative QCD. Now this perturbative QCD resides on the hope that if this is the contribution from the leading term, the contribution for the next to leading order term, or the contribution from the next to next leading order term will get decreased, such that after considering sufficient terms, we can truncate the series and say that all the other terms left behind doesn't contribute significantly. But this is only a possible scenario when this strength we were talking about is much, much less than 1. But what happens if this strength is comparable to 1, or not that small, not really that small? Then we need to include more and more and more terms, and we cannot really truncate the series. So let's see what happens for the strong interactions. That's a schematic diagram of how the strong interaction strength behaves with the length, and it can be shown only at a very smaller distances, that is only at a very high energy scale. The coupling strength is very less than, very less than 1, and that is when the perturbative QCD can be basically applicable. However, when we increase the distance or we decrease the temperature, we cannot really apply this perturbative QCD. So we can say that this perturbative QCD is not applicable for lower temperatures. However, we also have numerical simulation at our hand, but like all other numerical simulation, this lattice QCD also very much numerically involved, and they ask for technologically advanced computer to calculate. So what can we do if we want to look into the physics, but without getting into the complicated mathematics? And that's when people talk about the effective model. The main idea behind forming an effective model is we will look into a specific energy scale, and we will keep in mind the basic symmetry properties of our fundamental theory. Now, there are two main properties of this quantum chromodynamics. Number one, that I have already mentioned, that inside the hadrons, quarks and gluons behaves like free particle, yet they are not coming out. And that property is what we call the confinement property. And another interesting scenario that QCD shows is that the quarks, as we have said, the quarks are the constituent particles of protons. They are free masses of the order of 5 MeV, around 5 MeV. However, inside the hadrons, their effective mass becomes almost of the order of 300 MeV. That is known as dynamical mass generation. So when you are creating a model Lagrangian for QCD, you need to keep in mind that these properties also should be reproduced in your Lagrangian. Keeping those things in mind, the model Lagrangian for Polyakov-Nambuजना-Lacinier model is formed like this. Here, this Lagrangian shows the only dynamical quantity in the medium is quarks, because only quarks has this kinetic term, wherever the gluons are taken here only as a background field. And the interactions are so chosen such that we can reproduce the symmetry properties, as I have already mentioned. Now, with this thing in mind, if it's working well, let us calculate some bulk property of the medium. For that, we calculated the coefficient of shear viscosity. Now, this is an already existing plot where where the shear viscosity by entropy density ratio for various fluids has been shown. Here we can see that all the fluids showing a common behavior, that is, they are showing a minima near the transition temperature. Can the model we are using can reproduce this data? That we have seen that here also our eta by S plot with temperature is showing a minima near the transition temperature. So till now we are satisfied with the model structure. However, while calculating the shear viscosity, we have seen that when incorporating the medium interactions, those are going on inside the medium, we can only take into account the interactions where quarks are taking parts. However, if you want to take into account the gluonic interaction term, the gluon background field won't be enough. Then we will be needing some dynamical gluonic degrees of freedom inside our model. So to do that, we next looked into a model where along with this is a partition function. A partition function is from where you can evaluate all the thermodynamical quantities starting from your Lagrangian density. And here we can see this theta psi and theta psi bar are our quark field, and here we have the distribution function for quark and antiquark. Along with that, we have in this model a distribution function for gluon. This is a term for distribution function for gluon. And just as the quark field, the distribution function for quark is getting modified due to the presence of the background field, this phi and phi bar, here in this model, even the distribution function for gluon is also getting modified due to the presence of this background field. So now we have a model when we have both the dynamical effects due to the presence of quark along with the dynamical effects due to the presence of gluons. Now, this model were there in the market for long, but it was not used popularly, because if one try to do from here, unless calculating the path integral, if someone does the mean field approximation and try to approximate the result of this using only the average value, this model used to give unphysical results. We suggested that unlike doing this mean field approach, we suggested to do the path integral formalism for this background field method. When we did this, we have seen that for the pure gluonic case, our model result. Okay, our model result is in perfect agreement with the fundamental lattice QCD result that we have talked about before. And similarly, when this is for the pure gauge system, that is only the gluons are present in the medium. And when we included the quark sector as well, we have also shown the comparison plot with quarks and gluons with the lattice results, and we can see a good agreement between the two. Now, as I have already mentioned, any model should reproduce the symmetry properties of the quantum chromodynamics. Here we have shown that in this plot, in the left plot, here along the y-axis, we have the dynamical mass of quarks, and we can see at the low temperature where we have the Partenic region, that is a free quark mass, there this dynamical mass is very less, whereas in the low temperature region, that is when we are talking about the hadrons, so inside hadrons, the dynamical mass is high as expected. Here in the right panel, we have plotted a quantity that is the average of that background field. Now, this average of that background field for the pure gluonic case can be shown theoretically that it acts as an order parameter for confinement-deconfinement transition. That is, to put it simply, that is when this average of phi goes to 1, we can say the medium is deconfined, and when this average of phi goes to 0, we can say that we are in the confined zone. Here, due to the presence of the quark, this phase transition transferred to the crossover transition. And we can see that this order parameter smoothly goes from 0 to 1. And that shows that we have achieved a confinement to deconfinement phase transition within our model framework. We have tried to see where the phase transition is occurring by plotting where this change of dynamical mass or the change of average of phi is being maximum with temperature, and from this average value one can estimate about the phase transition temperature. So now that we have a model that has both the gluonic sector and the quark sector, both are sitting on equal footing, then we can hope that using this model should be used instead of those background field model, and this model can be used to predict the results where we can avoid the mathematical complexity, although in certain temperature range we can see the significant physics very well. And ultimately that is the aim of any physical work. So that's where we stand right now, and we have future plans to use those models for various other studies. So thank you.
Now, all of us. Subhendra?
Yeah, Prajita, it's an interesting talk. I don't understand all the things that you have talked about, rather most of the things. But I just thought that you draw some mathematical formulations and theoretical aspect to address this interaction, and try to get a unified model to explain all the results.
Yes.
So I just wondering, the data that people get in the CERN collider and other way can be supportive to your model, or you can verify your model there from the data.
Yes. From the theoretical, there are certain observables from the experiments and certain observable from theory that you can tally. We can have some experimental prediction for shear viscosity starting from some experimental data, and one can actually directly tally the theoretical result to the experimental results, depending on which are those connecting points where we can tally them. So that can be done. Obviously, that can be done. I haven't done that yet because so far I have done with the comparison from with the fundamental theories.
Arnam?
No specific questions. Okay.
Gautam?
Yeah.
Yes.
One or two things. First of all is that if you can do lattice QCD, then why bother with this model? Because you compared with lattice QCD, you have to go beyond. Otherwise, of course, if lattice QCD is definitely physically more understandable in the sense that, of course, it's very costly. But if someone can do lattice QCD, you are comparing with that. Have you done some calculation which goes beyond that?
No, not yet. Okay. Yes, not yet. But see, whenever I am developing a model, first thing I need to check is that wherever I have the data from the fundamental results, they can be reproduced from our model. And then the next step is that let's try this model where we cannot have. Yeah, next try, because we know for lattice QCD is yet not very successful to do the calculation for the finite baryon chemical potential range, and that is our next plan, to include the baryon chemical potential and do the studies.
Okay. And second question is, what will be a limitation? How, for example, at what density will it not work?
Obviously, one thing is this. First of all, the model studies always gives you qualitative results. We should not expect many quantitative details from a model study, because the models are always.
Do you also expect, for example, say neutron star to transition from your model? Surely not.
Yeah. Sorry, cannot hear you.
No, yes, I understand that model study can give you only some not exact results, but my question was, where will it fail? Not even qualitatively. Is there any limitation of your model that it will fail here? Can it say, for example, produce that? If you are looking at that picture for the first or second slide, that's for neutron star or Kaga superconductor. Can all those things be given out from your model or not?
That one thing that about this is, first of all, for neutron star and
No,
others.
you are looking for QGP to hadron gas transition. My
Yes,
question was
yes.
whether it can be whether this model will be working for the other areas also.
For that we need to do that, like for neutron star we need to do the studies on finite chemical potential, and then we can see. However, every model has some inbuilt every model has some inbuilt scaling inside it. Like whenever we do the momentum integration, there are some momentum limitation where we can. So a model like the fundamental theory is applicable for throughout the range, but for model we are always specific up to some temperature range where only the effective interactions we are talking about. So
Right.
obviously there are
I was asking what is your range for the model?
Oh, it's a quantitatively.
What is the range
Quantitatively, I
you are?
cannot specify it right now.
Ranjan? Prathita, I have a question. I didn't understand much. But in a biological membrane, you see that there is problem of phase transition, and that reflects in different types of biological functions. So
I'm sorry, I cannot. Pardon, I cannot hear you properly.
Yeah, in a biological membrane, we see that if we put some like changing cholesterol content or something, we can, or changing the temperature, we can put a phase transition in the biological membrane. So in your model, how you can translate in the biological membrane? Do you kind of have any bearing on this kind of biological membrane of your model?
So in biological membrane, you are talking about this core gluon phase transition?
Right. Because we can see that phase transition if we simply change the cholesterol, or if we simply change the temperature, and that has some bearing on the biological activity.
Okay.
So whether your model can be has any bearing on the biological membrane.
I haven't thought of it till date, but I can check it and come back to you later.
Okay, thank you.
So, Procheta, this is other Gautam Basu. Thank you for giving the talk. I just have one question, which is, your model, does it give any new insights? For example, when you try to fit simulated data or real data with your model and you see fit, sometimes, when you do not go for quantitative, like, computational work, models sometimes can produce insights. Did you ever think that something is not fitting and that is actually giving an insight?
Okay, now because till now the model studies we have done, it's to that range where we already have some fundamental results from the fundamental theory. But now that I have checked the model, we can go beyond where we can, I mean, we can approach the spaces where the fundamental theory is not yet successful to do. There we can obviously hope to get some new physical insight at least.
But have you seen any?
Not yet.
Okay.
I mean, we have seen all those physical insight that are already had been predicted from the fundamental studies.
I saw it. So my question was, anyway.
Yeah, then we need to check those regions to where the fundamental studies are not yet been done.
So thank you, Procheta, for a provocative talk for gluon interaction. We're going to move to our last talk. This talk will be given by Oyon. Oyon hopefully is here around somewhere.
Yeah, am I audible, Gautam?
Oh yes, with lots of noise and information.
Okay.
So Oyon is going to talk on noise and information in network motifs. Oyon.
Procheta, please leave your slides. Okay, thank you, Procheta. So, hello everyone, I'm Owen Bishar from the Department of Chemistry, and today I'll be lecturing on the interplay of noise and information in network motifs. So you can expect some crosstalk between statistical physics and biological signal construction. So I'll first introduce you to the model systems, that the gene transcription regulatory networks, and then randomness, which is inherent for a living cell. Then I'll present my data interlaced with some basic concepts. For example, the network motif we have studied is a feed-forward loop motif, the noise and information processing within it. And then I'll introduce the information decomposition principle for you. And afterwards, I'll give you two different types of information frameworks so that you can have a similarity between them. So this is a typical bacterial gene transcription regulatory network for E. coli. You have those genes and transcription factors as nodes and interaction between them as edges. But it can be anything, maybe epidemic spreading through population, or maybe the financial stock market. For us, it is small network motifs, that's recurrent patterns inside these huge chunk of interactions. So you have environmental signals interacting with genes through the transcription factors acting as mediators. And as I mentioned, it can happen in transcription networks, in synaptic connections, in ecological food wave, or even logic chips. So you have these activators. When signal is present, suitable one, it can bound to the genetic promoter, helps out this RNA polymerase to read out the information from gene. mRNA transcription increases, consequently the protein production increases. So it's a non-equilibrium phenomena. So this joining the promoter is limited by diffusion. Whenever you have thermal fluctuations coming in, it falls off. So you have a fluctuation dissipation type of relation, just like a Brownian particle attached to a heat bath. With the advent of single cell data, people expected that with the same set of genes, similar cells will behave identically, but it never happens. They have isogenic heterogeneity. So you have similar set of genes, different cells expresses differently all the time, but they use it to better perform in a dynamic environment. They do self-head choice for using it. They use it for antibacterial persistence. For us, we will be discussing these noise effects in our work. The first question we asked, so these are feed-forward loops. You have transcription factors, the master regulator S regulating X and Y, and X is the co-regulator targeting the final gene Y. So you have 8 number of them, coherent 4 and 4 incoherent types. The question is, nature only chooses this coherent type 1 and incoherent type 1 and rejects others. The question we asked, what is the reason behind that? Okay. Now we wrote a master equation for you. So you have some gain terms and loss terms, and you have a difference between them. You have the production rate parameters, Fs, Fx, and Fy, and the relaxation rate parameters, μs, μx, and μy, and the influx and outflux through these S, X, and Y copy number states gives you the DDT of the probability of being a single state. Now, you can write analytical expressions of the variances and covariances of it. Now, these are analytical expression, closed form, no series, no limits, algebraic equations. When you have these interconnections, the coupling between S and X coming into the covariance of Sx, and when you have the covariance of S and the final gene product Y, and you can actually visualize it through the sum of a direct integration, that is S interfering with Y, and an indirect one, that is the intermediate producing your final gene product. Well, so far so good. For this specific problem, FFL problem, we devised this size-independent formulation of extrinsic noise, that is the population normalized covariance of XY. And it has got everything around it, like 32 possible combinations is within it. You have these regulation signatures, you have OR gate and AND gate within it, you have timescale separation into these filtering functions phi ij's, you also have the steady state probabilities of the promoter being in on state or off state, right? Now, here is the result. So with respect to the population of S, you consider the extrinsic noise combinations for coherent 1 to 4. And the abundant one, the coherent type 1, gives you the highest amount of extrinsic noise. Everything falls flat beyond that. Okay. Now, this is for OR gate. For AND gate, again, now this is for incoherent feed-forward loops, OR gate. Again, the abandoned module gives you the highest amount of extrinsic noise, and everything is lower than that. So we conclude abundant FFLs transduce higher amount of extrinsic noise. Moving to the next question. There are 13 possible combinations of 3-node subgraphs in random networks, but nature chooses only FFL. Again, what is the reason? So we compared 3 of them, a cascade. So S-mediated production of Y is absent. You increase it and simultaneously decrease X interacting with Y. If they are equal, you have a feed-forward loop. And if this interaction, indirect interaction is absent, you have a fan-out. Okay? And in info, the entropy and mutual information. These are all random variables. The average uncertainty is your entropy, and the overlap between entropy spaces is your mutual information. Okay? You can also have a 3-variable avatar of it. And for a Gaussian framework, you can actually clearly interpret them in terms of their variances and covariances. Now, with respect to the tuning parameter, if you measure the 2-variable and 3-variable mutual information terms, nothing interesting happens. Okay? The direct contribution increases, indirect one decreases. FFL is something in between, but this is monotonic. You have inconclusive data to resolve it. You have conceived the fractions of mutual information, 2-variable divided by the 3-variable information for the direct and the indirect path. And Lavoie, you have maximized mutual information fractions for the parameters of FFL. Now the cascade and fan out are beyond this plateau. The output noise, that is the population normalized variance of Y, gives you a noise flow for FFL. And these high noise walls belong to cascade and your fan out. FFL acts as a better decoder of environmental signals. Much amount of your mutual information fractions minimize information output noise. So it acts as a better decoder. Now, if you transform their relaxation rate parameters, this one, and their population levels, you get some universality feature. Whatever you have got in the previous slide helps for this transformation. So you have universality popping out from this information processing scenario. Now, I'll introduce the multivariate.
Hello.
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 Yeah, I think just wait a little bit, Arindam.
Yeah, we can wait actually.
Oyan connection may be slow or something.
Yeah,
You may have lost it.
I've lost Iron's connection.
Oyan, are you there?
This thing gets stuck.
It's okay. He'll come back.
Okay. Yeah, am I audible?
Yes, yes. Yeah.
Yes, now you are audible.
Oyan, can you restart from that? You are introducing something called multivariate, God knows what.
Yeah, multivariate mutual information. Yeah. So shit happens. Maybe this one. Can you get it?
It's coming.
Yes, this one. Yeah, this one.
Yeah, you have minus.
Okay.
You have minus.
Okay.
You have minus
Okay.
2 minutes now.
Minus 2 minutes.
Okay.
ঠিক আছে আমি বলছি
Follow.
Acha, so let's begin. So you have this two variable mutual information, ISX and ISY, and whatever is in the overlap region is the common sharing of information. That's a redundant information. Whatever comes from individual contribution of this part and this part, that's the unique information from X and Y. And the outer region of enveloped by the three variable mutual information is the synergistic information. That's you get from the unison of the predictors, that is your X and Y, about your predicted variable, that is S. And actually you can write the equation, you can derive redundancy as the minimum of ISX and ISY. And at the end of the day, the interaction information, you check the balance between the total mutual information and the sum of the two variable mutual information. So that gives you a projection on the nonlinearity of information transduction. So the third project, I introduced this concept of different types of informational definitions. So this is the standard Shannon prescription, the log one. But the alternate one gives you the difference between the variance and the partial variance. And as a result of it, it's not symmetric, right? So for a two-step cascade, we compared all those PID metrics like unique information, redundancy, synergy, everything for these two Shannon and alternate prescription. With respect to this fitness, fitness is nothing but a function of the growing population of the signal, right? Now, you can see the y-axis are different, so the magnitude of these PID molecules are different, their trends are different. But if it really has to be a physical theory of biological system, it has to give some uniformity in its prediction. So this problem was solved by us. Probably I was the first. So according to the so what we did, we normalized each and every PID molecules with respect to their corresponding total three variable mutual information. And finally, you have similar types of magnitudes and the range of increment. And obviously, you have got a predictive similarity established between your Shannon and alternate mutual information. So we also did some work for the signal to noise ratio. That's the signal fidelity. What are the definitions for the Shannon one and the alternate one, and how you invoke the three body interaction into it, and then define gain. Okay, but it's heavy on calculation, but we also did that. So concluding remarks is efficient noise management and optimization of information processing may lead to some hint that why some of the motives, but not all, are selected by the evolutionary forces. And it's high time to look beyond Shannonian information and look for the biophysical meaning of these PID metrics. So I was reminded by this high energy talk. So with advent of high energy, you probe deeper and deeper into the atoms, and you unearth the intricate structures. Just like that, we have to consider these contributions from PID molecules. Now, I would like to acknowledge my mentor and my junior colleague with whom the FFL work was done. And these are the references for you if you have to know the complete picture. So yeah, so the first two are the FFL one. This one is my single author paper, the third project. And these are some of the information theoretic stuff which we did for diamond motif and a two-step cascade. So thank you all.
So thank you, Oyan.
Yeah.
So now, Shubhendra.
I actually missed most of the part of the talk, so may not I ask questions?
Okay.
So far as I understood is chaos and informations are necessary for cellular functions, and I mean that for a living cell to cell communications. I have a very naive question. Ayan, by applying your model or theory these things, can you regulate cell-to-cell crosstalks?
Yeah, actually people have done that. Like It's in a very recent paper, 2019 and 2020, physical review letter, physical review E. You have two communicating cells, right? Maybe they are similar, maybe they are dissimilar. Okay. Now,
yes, maybe they are similar, maybe they are exactly.
Yeah, it's a very recent paper. Yeah, you can do that.
Different cell, but within the same tissue. Just designate the cell A and cell B from the same tissue.
Exactly, and the bonus point is the researchers studied them in terms of phase transition. So you have a Landau type of formulation coming in, and order parameter. That's basically you project the equations of motions in terms of their biochemical parameters, and you have at the end of the day signal transmission and information processing to get maximized when they reach a critical point. So it's very exciting field to study.
And if it is some different type of cells, for example, cells from tissue A to cells from tissue B.
Exactly, but that information
phenomena will be observed, but I mean that your equations are. Can you generalize these things, or these two things are different for different types of cells?
No, professor. These are completely generalized metrics, and whatever you are talking about, if the cells are different, you only change the coupling parameters. So, for example, the two-way system, for example, cell A to cell B, if the parameter is, for example, GAB, and the other one is GBA. If they are same, so GAA GBA. If they are not, you put a non-equality inequality sign between them. So this is completely generalized stuff.
Thank you.
Gautam?
Yes, I think there is a graph showing the noise. Next one or something. Next slide.
Noise is
going
just
down.
noise.
The noise going down.
This one?
Yeah. So I was asking, since I am not really from the field, I was wondering why exactly. Can you physically tell us why this goes down at this point?
Yeah. So that's a very interesting question. So you see, the stochasticity in a living cell is primarily generated through the small copy number effects. So if you have a low sample, okay, so you have statistical fluctuations coming in. So these are basically 10 to 100 copies of gene products in a typical cell, right? So this type of fluctuations is there always. This is the intrinsic noise. Now, the output noise that we conceived is basically variance of Y divided by the S-mediated production of Y into the X-mediated production of Y at steady state. Now, YS is increasing. Now Yx is basically Y average, the total minus Ys average, because Y average is fixed. So you have a concave down. This basically you have like 1 minus x square in the denominator, right? You have that type of formulation over there. So if you increase Ys, so there will be something in between that will be minimized.
I see. How exactly do you define noise here?
Yeah, the definition of noise is very contextual, Professor. For example, if you want to have a size independent measure, for example, you can increase the population levels of these gene products, but the noise, the interaction between them should be constant, right? Because you basically transform everything by a multiplicative factor. So generally, you divide the variance by its mean or mean square. Mean square is general, so you have a Fano factor and Fano factor divided by the population. So it depends on the question that you are asking, but it has to be a size independent measure. If you have your cell and a cell from say an elephant, when we'll be calculating the noise, we should be removing the fact that you are tiny with respect to an elephant.
I see. But dividing by Fano factor means it is size independent?
Yeah, it has to be size independent.
Ranjan? Okay. So, I didn't understand much, but only you had a passing remark on Leuden and in relation to phase transition. Is that right? you make some
Yeah.
possible remarks on that.
So you
So
have this.
basically, you can study membrane fluidity in that way, right?
I hope so. The membrane physics, you have to have a basic understanding of mechanobiology, I guess, if I'm not wrong.
Okay, but
But
by
please.
your by application of your method, is it possible to study the membrane fluidity of a
Yeah, people from National Center for Biological Sciences, Madan Rao group does that. They have this formulation of they have recent papers from Madan Rao's lab on information theory applied to this mechanobiological problem. I think this is important from them. Yeah, translated.
okay.
Yeah,
Okay, thank you. Thank you.
thank you, Professor.
Hi, Oyan. This is Gautam.
Yeah.
I have a quick question. Do you
Well,
think our ancestors were more noisy than us?
in anthropocentric point
No,
of
no.
view, or
I won't tell you. Just I won't explain my question. My question is, do you think our ancestors were more noisy than us? Maybe in the context of evolution you talked about.
yeah, because we have a primitive life forms, and let's say unicellularity was there, and then we have multicellularity, right? So the noise propagation has kind of reduced with respect to that. You have a single cell, you have more noise, right? So from that point of view,
I
they
don't know.
were more
I
noisy.
think I think we need to sit down with a drink to discuss this. It's not
Yeah,
so
sure,
familiar,
sure.
is it?
Anytime.
Anyway, thank you very
Yeah,
much. I think this
thank you.
closes this session. I would like to thank all speakers, 4 speakers that we had before lunch, 4 speakers we had after lunch, and everybody and anybody who cared to listen to the speakers. Thank you very much. We will see you again next year. Okay. Yes? Okay. Thank you.
But you
Bye.
have to chat there, no?
Yeah, and I would like to ask the committee members to meet in the other Google Meet, okay? Right now.
Oh, sure.
Right.
কি হলো
Thank you.
শুনতেই পেলাম না সবাই লেফট হয়ে গেল আমি কি কে তোমার থেকে আমার আর আওয়াজ আসছে না হ্যাঁ হুম আমরা জয়েন করে বসে আছি কেন